One of the things that you can use triads for is attributes, specifically for attaching code to a cell. A cell can be attached as either a formula or as an event. In either case, the cell that we attach to is called an anchor cell, or sometimes a result cell. If it's attached as an event, then each time I change the anchor cell, the code gets executed, and at no other time. This code has to be incrementing the value in the last cell. A formula is more like a spreadsheet formula. The value of the computation, the result of the computation, is stored in the anchor cell, and each time you change something, the formula gets reevaluated in the cell. Gets a new value. Each formula or event has a wave of execution associated with it. This is the wave viewer down here. It's kind of a cluttered display, but focus down here. There are four stacks, 3 data stacks and 1 execution stack. Code begins when a cell is pushed onto the execution stack, X. Since that cell contains a value, it's not an opcode, it's simply popped and pushed onto a data stack when it's executed. We then follow a list of relative paths to find the next cell to execute, called the next route. The default route is left to right, top to bottom. So we find this next cell that contains 7, and we push that onto the X stack. That completes one cycle. X is executed by popping it and pushing it onto a data stack. We then follow the route again and find the multiplication opcode. When that's executed, it multiplies the value, leaves the answer on the stack. We try to find another cell, we fail, we get one end opcode pushed onto the stack for us by the system. And when the end is executed, it pops the value at the top of the A stack and uses that to set the value and the type of the result cell. In order to implement higher order functions, we need to be able to quote code. The way we do this is by pushing it into a grid. So these two programs are identical or equivalent. The bottom one, when it's executed, it pushes a 6, it pushes this grid, and then the evaluate opcode pops the grid, takes the first cell, pushes it on the X stack, and and off it goes. So this is the first program I want to show. This is an average computation. In the middle is the anchor cell for the result. The bottom is the formula, and the top is the input. Each time I change one of the values in the input, the formula gets recomputed and the result changes. This code begins by referencing the input cell and making a copy of the reference. And then it uses the higher order function fold, which is like reduce in the MapReduce paradigm, to fold in the addition operator into the list, producing the sum of the values in the list. Then we step through the list, incrementing this value here to get the count of the values in the list. We divide, set the type, and we've got the average. This is the second program here. This is the first simplest thing I can come up with that demonstrates reflection. At the top we have the anchor cell oscillating between -2 and +2. The program begins by referencing a cell called the heartbeat that's constantly changing. It then drops that value, but because it referenced that cell, every time it changes, this formula gets reevaluated. We then get the anchor cell and either increment it or decrement it. And if you watch that, you can see the program is rewriting itself over and over again, changing that between increment and decrement as it hits the boundaries. For a more practical example, we have 99 bottles of beer on the wall. Only 9 here because that's all would fit on the slide, but in fact, the number is controlled entirely by that cell in the corner. Here it is running. On the left is the main routine. Down at the bottom, on the right, is a subroutine called bottles that figures out whether to print bottle or bottles, depending on the number when they're finished. If we wanted to understand what's going on in this program, we would stop execution, bring up a wave editor, and start editing the code, dragging some breakpoints into various points. Then we start execution up again. And run to the first stop point. Once we're there, we can drag cells off of the wave viewer to inspect them, drop them on a viewer there. Now we're doing a map operation on this 3-2-1 array to turn it into the text we want. We just finished that, and we can see that it changed to 3 bottles, 2 bottles, 1 bottle. And then we let it play through to the end, and right before the end, we'll go back to the anchor cell, so we can see that getting set as the last step. The final program is a tic-tac-toe AI. The board is over here, some controls here, and this is most of the code, well, a bunch of the code. While this is running, you can see some more stacks down here. These are the reverse execution stacks. Every operation has an inverse that's pushed onto that stack, and you can play the code backwards in limited cases. You could also see that it's going faster than this stack because each higher order function is causing many lower order functions to get executed. And there we've got that answer in one. Now, the core of this algorithm is a list of 8 lines, the 3 horizontal, 3 vertical, and 2 diagonal lines through the board, and 2 sets of before and after rules that win or block on a row. Any language that you would implement a tic-tac-toe AI in would probably have the same sort of 8-line array. What's different about Thyrd is that array was constructed by direct manipulation, by dragging the cells directly from the board onto the list being constructed to set the relationship between the list and the cell locations in the board. Future directions I'd like to take this. I'd like to continue to improve the UI. It needs a lot of work, but keeping the focus on direct manipulation, basically pen-based as much as possible, minimal time. The current implementation is in Tickle. It's concurrent, but it's not parallel. So I'd like to do a multi-processor implementation. So the next version, I'm working in an interpreter in Erlang, a browser-based UI in JavaScript, or whatever I decide to use it, do it in, and a RESTful interface in between the two. And there's a small REST server in the existing code that scaffolds this development. For the distant future, my initial motivation in making a reflective visual programming language was I thought it would be an interesting language to do genetic programming in or other evolutionary techniques. I'm particularly interested in programs that are written partially by hand and partially filled in by some machine learning approach like genetic programming or evolutionary programming. So building on the work currently being done in error detection and correction in spreadsheets, my blue sky ideal for this is that a programmer would normally go along specifying positive and negative test cases at various points in the code, and then for some portions of the code would say, mark this as to be evolved, rather than I'm going to write it by hand. I'd particularly like to see if programs like the tic-tac-toe AI, if you started them out with the line representation written by hand and let them evolve the rest of the code, if that would be an efficient way to do evolutionary programming. Okay. Again, the paper is online. This is the website for Thyrd, and finished just in time. If anybody has any questions? Thank you very much.